Hello everyone, we are going to study the chemistry or the inorganic chemistry part of 12th. Now see, we are going to start the D and F block elements. So first of all, we have to know what is D block and what is F block elements. First we will study the D block elements, okay? So the elements of periodic table which last electron enters in the D subcell always. That elements are known as the D block elements. And the F block elements as usual when the last element enters in the F subcell, that is known as the F block element. First we are going to study the D block elements. So the always remember, this is the common structure, general electronic configuration of D block elements. Okay, n minus 1 D 1 to 10, it depends on the electron. Like example, we can take a chromium, copper, and this is n into s to the power 1 to 2, because we know the structure belongs to 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, 3d10. This space I gave to understand you that the 3d10 can be placed here because it is a structure which follows the first 4s2 rule. The electron enters 4s s subcell. After that, it enters to the 3d d subcell. We'll see as example. Now see, we'll take one example. Okay. For Fe, for iron, its number is 26 in periodic table. Now 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay, a count we will get 26, 2 to 4, 10 plus 6, 10, 12, 18, and 2, 26. We got 26. Okay, now the 18, 1, 2, 4, 10, and 2, 12, and 6. That region, we know this is the structure of argon. Argon electronic in periodic table, the argon number is what? 18. So in place of this Fe, you can directly write it also Fe. You can write it as argon, also 18. Okay. After that, 4s2, 3d6. This is the structure which follows this path. Okay. The the last element enters in what? Which? D subcell. Always we have to enter the element in S subcell of 4 orbital first. After that, the element will enter to the D subcell. In every, if there is this structure, let's say if the without adding 2 here, we can't add here 10, and after that we can write it this type. It's wrong. Okay, always we have to write the S subcell first of the n minus 1 element. We have shown it here. N minus 1 D 1 to 10 into N S 1 to 2. This is the structure. Okay, N minus 1 D, and that is here also be 4. Okay, now we'll go for the next example. Chromium. Okay, see, chromium of 24. Okay, now directly we can write argon 18. Okay, after how many became? Only 6. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, 3d4. You think this is correct? No, this is incorrect, because see here, this is not a stable state. According to electronic configuration, this is correct. Okay, no problem. But according to the stable, this can't be stable here, because always the half bonded or full bonded, that can be stable. Now what we will do, in place of 2 we'll put here 1, in place of 4 we'll give the electron in 5. Now it is stable. Always remember, in D block and F block also, this type of structure we have to do. If the electron in one is full, another is one little bit gap in 1 and 2, then you have to balance it. Okay, after that it comments. But it's an exception case, only which shows in only copper and chromium. Okay, this for chromium, this now we'll do for copper. What happens in copper? Copper means 29 number. Okay, see, argon 18. Now what happens? 2s2, no, 2s2 3d9, 4s2. What happens? 4s2, it is not stable. We'll do it as 4s1 and 3d10. This is now in stable state. Okay. Now we'll go to the next. That is for zinc. Is comfortable? It's comfortable. Now see, don't get nervous. This is the zinc part. Okay. We'll see in zinc also. What happens? The argon is here 18. The plus 2 3d10. Okay. Selection of 4. And fifth, we'll write nickel of 28, zinc of 30. Okay. For nickel, that should be argon 18 and 4s2 3d8. Okay. Now if we reduce 1 here, it is 1, but 9. It is also unstable. So in this case, it can be stay stable. The general electronic configuration of D block element is n-1, D1 to 10, and ns1 to 2. Let's remember this. n-1, D1 to 10, and ns1 to 2. It means, let's say this is 3, D10, and n-4, s2. This type of structure. Okay. You can write it in this form. Okay, it's not a problem. But in stable case, it is not always in this form practically. Okay. Now the question is, why exceptional electronic configuration is found in case of chromium and copper? This one, copper and chromium. Before we have seen the copper right here. In copper and chromium, which copper number is how? 29, chromium is 24. Now for copper, the structure how is how the became D10. Okay, 4s1, and argon is here. Also here is argon 18 and 4s1 and 3d 5. Am I not wrong? Yes, it is okay. Okay. Now see why this is different from all structures. Only these two are if just too stable here to these two. Otherwise the structure will be in 4s2 3d9 and 4s2 3d4. These two, but these two are the wrong due to stability. We know there are two reasons. One is extra stability of half filled or full filled orbitals. I have told you before, if the state is in full or half, for S this is 2 or 1, it is stable here. Otherwise it is not stable. Okay, for this case it is stable. Now in P, if the electron have number is 6 and 3, then it is stable. Okay, in case of D, if it is 10 or 5, then it is stable. In case of F, it's 14 or 7, then it is stable. Okay, if the number of electron is paid is 7 or full or half, here also half or full, half or full, half or full, then this is known as stable. Okay, now another reason is greater is the exchange energy, more will be its stability. It means what? The number of electron they will share, the bond will more stronger. Now see, we can see the example. If you are a neighbor, then new neighbor, then if you give them curry and something, then your bond is stronger. Okay, if you gave your home's curry and they gave their home special curry, and this is the thing. Okay, there are two reasons why these two have exception. Okay, see, first reason is, and second reason, extra stability of full and half bonded state, and the reason is greater is the exchange energy, more strong is the bond. These two are the exception case, and these two are the reason of this why this stability requires. Okay, now see, D block elements are also known as transition elements. Only those elements are called transition in which the D subshell is not fully filled. Now see, in zinc, the D subshell is fully filled. Not only in zinc, but also in what? Cadmium and mercury. Cd, cadmium, and Hg, mercury. In thermometer, use it. Cadmium and mercury, the D subshell is fully filled. Like this type of structure is there. Okay, due to their fully filled D subshell, they are regarded as D block but not transition elements. Why? Transition element. The next word is transition elements. All D block elements are known as transition elements except these three: zinc, cadmium, and mercury. Why? Due to their fully filled d subshell. Okay, if the d subshell is fully filled, then that electron will not consider as what? Transition element. Okay, remember these three. This in this three structure, the d orbital is always fully filled. Okay, we will see further it as an example in our revision classes. Okay, now all transitional elements are d block, but the reverse is not true. It means all transition elements are d block elements, but all d block elements are not transition elements. Okay, due to these three exceptions. Now, why d block elements are also known as transition elements? Okay, this is the question. Why d block elements are known as transition elements? Let's say d block is present in between s and p block. We know. Okay, we'll rub it. The transition elements. Okay. See, the structure is like that. A block is there, D block is there, S and P block. We have seen in periodic table the structure is like that. The S block elements are here, the P block is here, the F block is in this type of structure in downward. Okay, F block is here and the D block is in the middle. Okay, you can see, if it is possible then open the periodic table, you can understand it. Now see what happens. The D block present in between the S block and P block. Okay, as we move from left to right, it means S to P. When we are moving from S block to P block, the D block is situated in the middle part. So the D block element's character changes from electropositive to electronegative. It means positive to negative. When we will move thoroughly from this part to this part, okay, the positive electropositive energy will thoroughly convert into electronegative energy. In S block it is positive, in P block it is negative. Okay, hence they are said to be transition elements. Okay, because the transition is happened here from positive to negative. That's why the D block element are known as transition elements without zinc, cadmium and mercury. Now see the transition series. There are four series. Okay, one is 3D, 4D, there is 5D. Okay, another is belongs from 89 to 104 and so on. Okay, now for the 5D, this is for 5D 57, 72 to 80. Now here 39 to 48. This from 21 to 30. It means scandium to what? Zinc. We have to remember all the elements in this 3D cell. Okay. This is known as first transition series. This is second. This third. This is fourth. Okay. These four are the series. Okay. Now see 58 to 71 known as, here no, 58 to 71, 58, 59, 60 to 71. Okay, 58 to 71 known as what? Lanthanoids. lanthanoids, and 92103. They're missing 92103. I think these are the actinoids. Actinoids. Okay, and these two are known as F flow. These are belongs to F flow. Okay. Next class we'll study about the these characteristics. Okay. Now we'll revise what we studied. The D block element normal configuration is n minus 1, D 1 to 10, and S 1 to 2. Okay, we know the general electronic configuration. We know the exception of zinc, cadmium, and mercury because they are not the transition elements. Not they are not the transition elements. The half and full subcell have the extra stability. Okay, these topics are we known. Go through the video and thank you. Meet you in next class.